Today we'll do an overview lecture, just about sort of the big picture. And we'll start with, I'll talk about a couple of things. I'll talk about just sort of what is optimization. It'll be very informal, so anything you're not supposed to be following, you're certainly not supposed to be following every detail of what I say today. Because everything we're going to talk about today, we're going to talk about later in disgusting detail. I mean, we're going to go through it. It's going to be much longer. So if you're not following something, that's fine. In fact, it's not even clear it's what we say is complete. Okay, so talk about optimization. I'll move on to least squares and linear programming. And these are really the most famous and the most widely used optimization problems, widely applied optimization problems that there are. By the way, they're both convex optimization problems. I'll then say just a little tiny bit about the common parent, and the common parent of them is convex optimization. We'll look at an example, and then I'll have some general comments about what are we going to cover in the course, what are the goals, what's the style, all that kind of stuff. I'll say a little bit about nonlinear optimization. That's something we're not going to talk about much in the class, but just because it's weird not to say something about it before launching into the class. And then I'll finish up this overview with a little bit of a history of convex optimization. Okay, mathematical optimization. Well, an optimization problem. Now the notation is this: is you say you minimize a function, an objective function, subject to some constraints like that. By the way, there's many other notations for this. In particular, the notation from the Soviet Union, where there was a long tradition of work on optimization, is this. You write a problem this way, and this is now in the U.S. From various people who were trained, say at Moscow State University, is you'd write F0 arrow min, and then ST doesn't mean such that, it means in this case subject to, and then you'd write Fi of x is less than Bi. Okay, so something like that. So you'll see other notations for it. One other thing I should say is, although minimize and subject to are English words, obviously, I don't consider them that way here. They're actually names of attributes in sort of, you can think of this as an object, right? It's an optimization problem object. Minimize is an attribute, which is the sense. It could also be maximize, of course. F0 of x is an objective. Fi of x are called constraint functions. Okay, now, so that's an optimization problem, and we'll talk about it in much greater detail later. So here, so these you have x here. That's called the optimization variable. So a lot of other names for it. Another one is decision variable, which is a great name because it sort of tells you it's something you have to decide on. You have a choice of different things. Then F0 is the objective function. F0 of x basically tells you actually how much that choice irritates because you're minimizing F0. And so if F0 of x is large, that means you're very irritated. And the smaller it is, the better. Okay? And then the constraint functions have a different semantics. All that matters with a constraint function is that Fi of x should be less than or equal to Bi. Often, but not always, these have interpretations like resources or something like that. So Fi of x is when you choose x, Fi is how much of the ith resource you use. And this constraint states that your budget is Bi. Okay? Now, a solution is simply a point x which satisfies the constraints, and among all those that satisfy, all the vectors that satisfy the constraint is one that minimizes F0, right? And you can call that an optimal point. You can also call it a solution. To be honest with you, optimal solution, that term, is redundant. It's technically correct. Stylistically, a better statement would be something like optimal x star or solution x star. Let's look at some examples. So the first one is portfolio optimization. So here, the variables could be the amounts. You have x1 through xn, and these could be the amounts you invest in different assets, right? So, by the way, these amounts could be number of shares, they could be dollar values, or they could be fraction of a total portfolio, right? So there's lots of, they could represent different things. Also, by the way, negative could be used to represent a short position, right? These are assets you borrow but have the obligation to pay back later. And that's essentially the same as owning a negative number of them. Okay, so these are the variables, right? And so you would talk about a vector x then in this context as like a portfolio vector or a portfolio allocation vector, right? So that would mean how do you allocate your budget across a portfolio, something like that. Well, the constraints would be things like this. Well, you'd have a budget, for example, everyone, I'd like a portfolio which is 10 to the 9, 10 to the 9, 10 to the 9, 10 to the 9, 10 to the 9. Everyone would. It wouldn't matter. I guess those can't be fractions, but if those were in any other amount, that'd be fine. But of course, there's the constraint that it has to, the total has to be less than your budget. There might be maximum minimum investment per asset. Very common is that it's required that the x's be non-negative, right? That means that you can't have short positions, right? That you can't have, you can't own a negative number of shares. That's actually required legally in a bunch of situations, like for example, mutual funds in the U.S. You can't have, you're just not allowed to own a negative number of shares. Hedge funds, that's false. You're allowed to. Okay, you might have another very important one would be like a minimum return, right? So you'd say, and that's of course expected return, right? So if there's a minimum guaranteed return, that's called an arbitrage. That's the religious basis on which modern Western economics is based, on the idea that there is no such thing as arbitrage. Actually, a lot of people at hedge funds will snicker and say, "Oh yeah, sure." Okay, and then the objective might be, so you might say, "I want 5% expected return minimum." Okay, and the objective might be to minimize the total risk in the portfolio, right? And there are many ways to give risk. It could be the variance of the return over some period. It could be something more sophisticated, like you want to make sure that the probability of a loss of a certain level is less than some number. Lots of different ways to give these. By the way, we'll end up looking at many of them. Okay. So here, what portfolio optimization does is it chooses the best portfolio that satisfies all the constraints and minimizes your risk. Okay. Next one is device sizing. So I guess that's from conceptual to and virtual to physical, right? So here the variables are the device widths and lengths. So all of you have lots of electronics on you right now. All of it was at some point designed by someone, and in particular, every device had the widths and lengths of all the devices were chosen, right? The lengths are often, in digital circuits, are often chosen to have the minimum possible value for that technology. Actually, not always, but usually. So that's chosen. And the basic constraint there is you can make a big old wide device. There will be like a wide gate, a wide transistor, and it will be really fast. That's the good part. The bad part is it will consume a lot of power, and it will consume a lot of area. Okay, so I mean this is just roughly the idea. Okay. Now the constraints are things like manufacturing limits, right? Because when you design a circuit, you send a big old file over to Taiwan, whereupon it gets sent to Pudong for manufacture, and it's just this giant file that describes in the standard language basically the postscript of circuits. It says this is my physical circuit. Please manufacture it, right? So, but when you manufacture it at a certain fabrication facility or fab, they'll have limits, right? This length can't be it can't be smaller than 22 nanometers, something like that, right? So that's how that works. Okay, or it can't be larger, and there's actually very complex rules, but the basic ones are minimum and maximum, things like that. This is very important. You have timing requirements. So timing requirements is that, well, it basically says your circuit has to work. Okay, it has to work at whatever clock speed it needs to work at. So if it's going to clock at 1.5 gigahertz or gigahertz or something like that, then it says in maybe 80% of a nanosecond, once the clock flips and the signals start running through the various gates and things like that, you have to have stable values with some margin before the next clock tick, which will come 1 nanosecond later to gigahertz, right? And so there, if you make everything minimum size, all the devices minimum size, the good news is your chip will be very small and it will consume very little power. That'll be great. And the only minor problem is it won't work because it certainly won't clock at the speed you want, and it may not even clock at a much slower speed, but in any case, it's not that interesting if it clocks at 150 megahertz, right? As opposed to whatever it's supposed to. So these are timing requirements. And of course, you might have a maximum area, right? So total area, you might say it has to be no more than 2 square millimeters, period. And that drives a lot of economics of chip design and stuff like that is based on area for obvious reasons, right? Okay, and the objective might be among all designs that satisfy the timing requirements, everything else might be minimize power consumption. And that would be a good thing to do for many reasons. But for portable devices, it has an immediate and obvious good effect if you have low power, because it means long battery life or something like that. So that's great. Okay, so that's your second example. And here, if you apply optimization to this, which is basically what is in fact done, what happens is among all designs that meet all the constraints, you find one that has minimum power, right? So that's kind of the idea. Okay. And the third is actually from a different category. It's data fitting, right? So it's got lots of other names. It's also called, for example, statistics. Another name for it is machine learning. And we'll see lots of others. Estimation. Okay, so these are all names for kind of the same thing. But the idea, and we'll see lots of examples of these, by the way. But the idea is something like this. Here, the variables that you're deciding on, note that the variables up here are things that kind of translate into actions, right? So, for example, up here in the portfolio one, X3 is the amount of asset 3 to buy. That would translate, well, in the old days, into a phone call to tell someone to buy 3 shares of something or whatever, or, but some number of shares of something. And nowadays, it ends up with a fixed protocol packet that goes to some trading computer and then executes a trade for you. Okay? So that's, so in other words, when you optimize, the result of the optimization is there's an action. Okay? And the same is here. Same is true here for device sizing, right? You finish the optimization, and the result is this gigantic file that describes physically your chip, and that gets sent off to TSMC or wherever it's going, right? So that's how that works. It gets sent to a fab to be made. Okay, so these are actions. In data fitting, it's quite interesting. The variables represent model parameters, and they don't correspond to any action whatsoever. There's no action, right? So the variables are model parameters, and the constraints. So in other words, you have a family of models to describe some data, right? I mean, well, that's what statistics is, right? And then your constraints might be things like prior information. For example, some of those parameters might be non-negative, and you know it, right? And you won't even entertain a model. You won't even look at the idea of a model where those numbers are negative. Another part of the parameters might be, for example, a covariance matrix, right? So in there, no one would ever even entertain a method that estimates covariances and occasionally comes back with a matrix that's not positive semi-definite, right? Just doesn't make any sense. Okay, and the objective, well, there's a couple, so this is simplified. But the main objective is actually just, it could be something like measure of misfit against your data, right? So, and we'll see lots and lots of examples, right, for classification, in regression type problems, and just general estimation, where you want to estimate some parameters, you have some measurements, and then the question is, from the measurements, how should you estimate the parameters? By the way, it has lots of other names. Classically, in kind of older approaches to this, it's sometimes called inversion. Estimation even has kind of an older sound to it. It sounds like it's from the 60s or something like that, right? But the modern method is to set up an optimization problem and solve it, right? You say what you want to minimize, and then you do it. if the problem is solvable. We'll get to that. Okay? So, and this, we'll see a bunch of cases like this. What's very interesting about this example, though, is that here the variables are not actions. They're parameters in a model. Okay. So how do you solve an optimization problem? Well, I should say, I should mention there are the childish ones that you were subjected to when you were taught calculus, right? So this is kind of this 19th century view, right? Yeah, it kind of works. That's like you set the derivatives equal to 0, and there's like 21 problems like that you can actually solve, and fine, whatever. Okay, so there are these cases, right? And we shouldn't deny that these cases exist, but it's not particularly interesting, in my opinion, in the current situation. Okay, so most of them are basically very difficult to solve, and in fact, probably I could go further than that and say they're impossible to solve in some ways. If by solve you mean solve, and what you can do is you can change what you mean by solve, right, to mean, for example, not solve. Well, I'll get to that. We'll talk about that a bit later, right? So in fact, now the fact is, a lot of people use general optimization used all the time, right? Generally, but there has to be a compromise, in all cases. The most usual compromise is to not always find the solution. So that's local optimization or something like that. And it means you simply run an algorithm that does something and may or may not produce a point that's feasible and has an objective value that's lower than, I don't know, it might have been, or often you compare it to a starting point or something like that. And that's fine. And that's quite useful. Now, if you do insist on actually solving the problem, like actually finding the global minimum, then what happens is these problems can have very long computation times, right? And there are other cases where that is used, not anywhere near as many. Okay, but there are exceptions, and the exceptions, they're very famous classes of problems where there are exceptions. And the most famous one by far is least squares. So in least squares problem, that's an optimization problem, we'll talk about it shortly, you solve the problem. You don't, there's nothing about, sometimes it works, it often works, it really works well. It just works always, period. Okay? So that's least squares problems. Another one is linear programming problems. That's another very famous and broad class of problems. And the common parent of these two, which is a lot broader, and it's what this class is about, is convex optimization problems, right? So that's the common parent of these. And these are problems where they can be solved efficiently and reliably, right? And so, I mean, when you start getting into some details, there's a lot of exceptions there and qualifications, but roughly speaking, this is correct. So let's look at least squares, just to look at what one of these things looks like. It's a very simple problem. Looks like this. It says minimize the 2 norms squared of ax minus b. The variable is x. By the way, that's part of it. You have to say what the variable is. And then a and b are data or parameters, meaning that they are the ones that tell you what a problem instance looks like, and you have to instantiate a and b or specify them before then you have a problem instance, and then you solve it. Okay. So that's that. I'm assuming it would be everyone here has seen least squares in probably, I would hope, in multiple classes, because it comes up in tons of classes, or it should. It might not have looked exactly like this in those classes, right? All right. Well, this problem, I mean, I'm assuming no pathologies here. I mean, A is, for example, tall and full rank. Then there's just an analytical solution to it. It's just A transpose A inverse A transpose B. Right, so that's it. That's a good chunk of what we did in EE 263, and I might add many other classes. Right, in statistics, it's called regression. Okay, it's got lots of names. All right, analytical solution, which, by the way, doesn't mean a whole lot. Right, there are plenty of things that have analytical solutions that so-called analytical solutions that are impossible to actually compute. And actually, this whole course is about lots of problems where there are no analytical solutions and they're very easy to compute. And that's kind of what this class is. Okay, so more than simply being there's an analytical solution. There are reliable and efficient algorithms and software to solve least squares problems. By the way, it's not trivial, and not one of them uses the analytical solution directly. In other words, I'll tell you what you don't do. What you don't do is form A transpose A, then form its inverse, multiply it by A transpose, then multiply it by B. That's not how it's done. I mean, obviously, it's not done a whole lot different from that because it's just evaluating this, but still. Okay, and the computation time is proportional to n squared k. N is the size of x here, and k is the number of rows. So if this is a regression problem or something like that, you'd say that k is the number of examples or something like that, or data measurements or data elements, something like that. And then n is the number of features or regressors or something like that, right? And so the computation time is proportional to n squared k. That's if everything is dense. If A is sparse, it's a whole lot less than that, right? So, and I mean, this is absolutely amazing. You can solve problems that are really quite large and with total and utter reliability, meaning you will compute, in this case, assuming there are no pathologies here, there's actually a unique x that minimizes that, and you'll actually compute that point to very high accuracy very quickly, right? So, okay. So I would say that least squares is a mature technology, right? It's kind of cool. It goes back about 200 years because Gauss wrote a paper about least squares in Latin right around 1800 something or other, right in there. So a little bit more than 200 years old. Anyway, so and it's used like everywhere, right? So which I'm sure all of you know. Okay, so how do you use least squares? Well, you can't even ask this question like, is this a least squares problem? It's just not that hard, right? Here, ready? Let's figure out how do you test if a problem is a least squares problem. You first ask the following: is the objective? Are you being asked to minimize the two norms squared of something which is an affine function of x? Affine is linear plus a constant. And if the answer is yes, then you say yes, it's least squares. If it's no, then you say no, it's not. Okay, so there, that was the. So you don't even talk about this. I mean, what does it mean? So instead, what least squares, the way you should learn about least squares, and I mean, to some extent you get this, maybe better in the statistics courses than some other ones, but it turns out you learn a couple of tricks for least squares, whereupon you are very effective. One is the idea of weighting. So you have a bunch of measurements and you can weight some more than others. That's weighted least squares. And then the idea of adding regularization. We're going to talk about these things later in the course. But you know those two things and you are now very effective. And in fact, you can even say a giant pile of engineering, statistics, all sorts of stuff. Data analysis has been done exactly this way, right? So planes fly because of this, basically. Okay, so now they'll fly better when more people know the topic of this class. That's already kind of, but we really have to say this stuff, least squares, you can do a lot with it. So, okay. All right. So linear programming, let's talk about that. So linear programming, that's this problem. You minimize a linear function of a variable subject to some constraints which are a linear function less than a budget. Okay? So we'll talk about this in great detail later in the course. That's a linear program. This is also not new, by the way. For example, Fourier wrote a paper about this, I don't know, 1820, something like that, long time ago. Okay? So, but the modern era really traces to about 1948, 1950, and by the way, has a Stanford connection, right? Because it was George Danzig who popularized it worldwide. It actually, more honestly, it has a Moscow connection because that's where it was really done first in the 30s. But anyway, this is linear programming. We'll talk a lot about it later. But here's the interesting thing. There's actually, except in completely trivial cases, there's no analytical formula for the solution. Okay, there's nothing like A transpose A inverse A transpose B. Okay, I mean there are for completely trivial special cases, right? But in general, no, there's not. Here too, there's reliable and efficient algorithms and software to solve linear programming problems, and it's just as reliable as least squares. Maybe not just, but it's very reliable, and it's used everywhere in almost all mathematically sophisticated fields. By the way, there are still a few kind of backward fields where it hasn't penetrated yet. It's coming. If you know anyone in one of those, you have a friend in one of those fields, just tell them, why don't they bring linear programming into it? Well, we'll see. We'll get to that later. Okay, so now the computation time, this is very interesting. It's just like least squares, right? It's the same. It's the number of variables squared times the number of inequalities, and the number of inequalities has to be bigger than actually, it doesn't have to be, but typically is bigger than the number of variables, right? So same sort of thing. It's a small dimension squared times a big one. We're going to come back to that later in the class. If you remember nothing from the end of this class, it's small squared times big. But we'll get to that later, much later. Okay, so this is a mature, it turns out this is also, I would say, a mature technology, linear programming. I mean, it works. It's like least squares. What's interesting about linear programming is that there are many problems that don't look like linear programming, but that can be transformed to linear programs. And we'll see a lot of that in the course as well, right? But that's good and bad news, right? The good news is it means that something that looks like a pretty restrained problem, like the only thing it ever refers to is linear functions. But almost any interesting thing you can think of, there are nonlinear functions involved. And then you say, well, this must have very limited practical use. And that's going to turn out to be false for the reason I just mentioned, that there are a lot of problems that can be transformed to linear programming. That's the good news. Now, I don't know if it's bad news. I don't know. Maybe it's also good news. The good news is you have to know what problems can be transformed and how to transform them. And that's also going to be part of this course. Okay. So that's linear programming, and we'll go over this in great detail later. This gets us to, well, convex optimization. So I'll say what it is now. Of course, we'll come back later and do tons of, go over this in great detail. So for now, we're going to say it looks like this. It's a problem where you minimize an objective with constraint functions, and all of these functions have to be convex. And that just means that this inequality holds here. It says that if you take a weighted average of f and of x and y, and you evaluate the function there, that's less than the same weighted average of the function values. And that's basically a picture that looks like this, right? It says that if you take x here and y here, and if you take some combination like alpha is 0.25, beta is 0.75, and you go here, then it says that if you evaluate it at that combination, that mixture, the function is less than just the same mixture of the function values, right? Or to put it in classical language, you'd say something like this: the chord lies above the graph. Linear programming and least squares problems are special cases, right? Because the graph of norm ax minus b squared is like a bowl-shaped thing. I mean, if you slice it, you get ellipsoids, and it kind of goes down like that, right? So, I mean, we'll see later. It's going to satisfy this. And affine functions actually satisfy this always, right? In fact, affine functions satisfy this inequality here with equality, right? So, or another way to say it is a convex function, and we'll talk about this in great detail in the next 2-3 weeks. Convex functions have non-negative curvature. They curve up, right? Affine functions, linear plus constant, they have zero curvature. They're on the boundary between, well, not convex and convex, right? So linear programming is sort of like the extreme case of convex optimization, because all the functions involved are just barely convex, right? Or like something like that, right? They're right on the boundary. Okay. All right. Now, in general, there's no analytical solution for convex, except for, of course, a handful of sort of trivial cases. And we'll look at some of those, and some of those are useful. But that's kind of not the focus of this course. But there are reliable and efficient algorithms. And the computation time, it's roughly the same as something like least squares. It depends, though, on various things. And we'll have a much more nuanced picture of this later in the class. But it's something like n squared m would come up, right? Depending on the sizes of various things. But in general, it would degenerate to this something like, for example, for linear programming, it would degenerate to the numbers I gave. And same for least squares, right? So that's what it would look like, something like that. And it's related to the number of variables, that's n cubed, the number of constraints is m, and capital F is the cost of evaluating all the functions in their first and second derivatives, something like that. Okay. Now, then the question is, how do you use convex optimization? Well, here's the first thing that's actually kind of interesting is this. It's actually not easy to recognize convex functions. And in fact, that's where you're going to spend the first 3 weeks getting up to speed on that. And in fact, not just the first 3 weeks, because we'll do it for 3 weeks and you'll be all overwhelmed and stuff like that. But then for the next 7 after that, in practical context, you'll be doing absolutely nothing but recognizing convex functions. Nothing. I mean, that's basically what the class is about. Okay. So, and it's just not that, it's not obvious. We'll get in. We'll see some. We'll see what that looks like later. Okay. And there are some tricks. There are some tricks. We will see a bunch of them where, for example, a problem might not be convex in its original form, but then it turns out you do some transformation and now it's convex. And the implication is now it's easy to solve. Okay? And a good example is that circuit design that we talked about. It's not convex in the lengths and widths, but those are what you're supposed to, that's what you're supposed to optimize. So what do? And it turns out, and this is not at all obvious, it is convex if you work instead of with the widths and the lengths, you work with the log of the lengths and the log of the widths. That's weird. Although actually, if you talk to a circuit designer, it's complete. They would say, well, duh, or something like that. And I'd say, yeah, well, why do you say that? And they're like, it's obvious. Or I don't know. Anyway, I trust them. I believe they know that, right? It's actually also interesting if you look at sort of like sometimes the widths and lengths are discretized, and they look like things like this. It'll be like 1, 1.4, 2. 2.8. Anyone know these numbers? 4. So they're geometrically spaced, hinting that somebody knew clearly that what mattered was actually the log of these things, of these widths, and not the actual values or something. So, okay. Another thing that's true is that, and that's another focus of the class, is that it turns out that lots of problems can be solved via convex optimization. So that's also part of this class. So we're going to look at a lot of them. By the way, a whole lot more cannot be. But that's another story. And we'll talk about that several times. Okay, so let's look at an example. So here I have a bunch of lamps. These are the lamp positions. And I have some surface down here, which is piecewise linear. And the lamps, I can choose a power at each lamp. And then that gives you an illumination on each surface. And the mapping from power to illumination is linear, right? So this is not coherent light. It's incoherent, and the powers add. Okay, and you just get some geometry factors. The geometry factors would be inverse square the farther you are away, and then you have a shading, or I think some people call it a cosine factor, right? So that if you shine light from here and it goes down, you get cosine theta is the effective power illumination on it. So okay. And the 0 says that if the surface is like this is the surface you're illuminating, and the source is there, you get 0 because it's under it, right? So, okay. And you can make much more sophisticated models that would look the same. For example, you could add mirrors and weird other objects and stuff like that, and it would still be linear, but it'd be a super pain in the ass to figure out what these coefficients are. Now the question is, you're going to choose the lamp powers. The lamp powers, by the way, have to be between 0 and some maximum power. And what you want is to achieve some constant desired illumination on the bottom. And we're going to measure that by percentage deviation. In fact, by maximum percentage deviation, right? So we're going to take the log of the actual illumination, subtract that from the log of the desired one, and we'll take the maximum of that. So that's basically the mini-max percentage error. That's the correct interpretation of the objective, right? So, okay. All right, so how would you do it? Well, and I'll just trace you through what I think would be a reasonable way to solve a problem like that. By the way, this is someone who actually wants to do this. This is not a theoretical analysis or something like that. So you might do the following. Just to get a feel for the problem, you would do this. You might set all the lamps at constant power, and then vary that power level and plot the objective and find at least find out what constant power level would do the best that way. Okay, you might use least squares. So you might do something like this. You might say, well, the idea is to make I desired, ik equal to I desired, right? I really want to make it equal in a mini-max percentage error, but screw it. I mean, one measure of being close has got to look something like another one, so I'll use least squares for which I have technology. Okay, so I'll use least squares. Now, the problem with this is if you do this, it's pretty much guaranteed that some of the powers are going to come out negative. And in fact, it's likely you'll do really well. That you'll really do well. Many of the IKs will be very close to the desired one. And the way you'll do that is something like this. When you go back here, these things will put out some power, and then to adjust it, like this guy in the middle will spray some negative power. It'll spray darkness onto the patches, right? And it'll just kind of adjust everything, and you'll do really well. But it's not relevant that you do well because it doesn't work. It violates the constraints. Okay, so then you would go into some weird mode where you would do things like this. You'd say, okay, I'll do least squares and get some lamp powers. And then if the P that's being called for in least squares is negative, I'll clip it off. I'll make it 0. I'll turn that lamp off, okay? And if PJ is bigger than my maximum allowed power, if my maximum allowed power is 10 kilowatts and it comes out as 20 kilowatts, I'll just clip it to 10. I'll do as much as I can, right? And if you're lucky, something like this might work, right? But if you want to do something a little more sophisticated, you would then come up with something like this. You'd say, well, I'll keep this here because that's what I really want. It's not what I really want. Sorry. This is already a surrogate for what you really want, which is the minimax percentage error, okay? And you'll add something like this. This is a standard trick in least squares. You augment the objective by adding in this. This says, I want my lamp powers to be right smack in the middle of the interval that they're allowed to be in, which is 0 Pmax, right? And so the point is here, these are like weights. That's a little knob I can turn. And if I crank up a WJ super high, what happens? PJ gets to Pmax over 2. I mean, nearly, right? Okay, but in particular, some way, as I'm turning that knob, at some point, PJ gets in the acceptable interval, right? So for these W's high enough, you get feasible. Now, of course, that's part of the objective. Meanwhile, this is getting bigger. And so now you could think of some methods for automatically adjusting these weights and weight twiddling and all that kind of, you could do some stuff, and something would probably work, maybe, kind of. Something would happen. It would work. By the way, this is how stuff is actually done, right? So, okay. By the way, if you're in statistics or machine learning and you're snickering right now, you shouldn't be, because same thing. This is just regularization, right? Although I guess cross-validation is pretty good. That no one can argue with, so that's fine. Okay, all right. Or you might say, well, no, I know about linear programming, and I can actually solve this problem. And now you're getting real close to the real problem, right? Because look at this. You can handle in linear programming these inequalities, and you can handle the max of an absolute value. So you're getting pretty close now to what you want. The difference is this is the minimax error, but what you want is in fact not the minimax error, but the minimax fractional error. So you're getting close. This would get you pretty close, especially, by the way, if the solution comes out and it's only like plus minus 5%, you're done. Why? Because between 0.95 and 1.05 log 1 log x looks like whatever, x minus 1, period. So you're done, right? Now, if it comes out plus minus 50%, something like that, that's not true anymore. But okay. Now, all of these are these are not solutions, right? These are approximations, right? So, but it turns out it's a convex problem, right? And it's convex. I'll say why in a minute, but it's convex because what you're really minimizing, if you take the x above it, is this thing. H is something like the fractional error, right? So it looks like this. If you're above your target 1, right, then it's just linear in it. Right? And if you're below it, it's 1 over it because it's something like that. So in other words, plus minus 2 would tell you something. That's the 50% point. And indeed, it would be the interval 1/2 to 2. Right? So that's how that works. And We'll see later that a sum of convex functions is convex, and so is a max and all that kind of stuff. So that would tell you this function is, this problem is convex, and you solve it exactly. And not only that, actually, with tools that you will learn in this course, this would be completely, you could, I mean, by the fourth week or something like that, this would be a joke for you. It would be insulting to ask you to solve a problem like that. And you could actually write a script that's about 4 lines long that would solve it, right? By the 8th week of the class, you could write your own, you could roll your own for this, right? You could write your own solver for it and stuff like that. So, oh, and by the way, the computational complexity is, it's a modest factor times least squares, right? So like 20, maybe 10, right? So what that tells you is if you do more than 10 weight twiddle, you know, if you twiddle around with the weights like 10 times and fiddling around, then it would be faster just to solve it exactly. That's what it comes down to. Okay. But let's see, let's add some more constraints and see what happens. So we'll add, we'll think about adding one of, 2 constraints. Here's one. No more than half of the total power is in any 10 lamps. I have no idea why you'd have a constraint like that, but let's suppose you did, right? Something like that, right? Okay, so, or no more than half the lamps are on, right? So suppose these are your 2, these are your, these are the 2 constraints. At first they sound like they're about the same. Certainly if you parse them in English, they sound kind of similar, right? They don't sound that different, right? And it turns out this constraint is convex. And that means it's immediately easy to solve exactly. This one is actually extremely difficult to solve exactly. By the way, there's very good heuristics for solving the second one. Approximately solving the second one. Very good heuristics for it. But they're just heuristics. Okay? I mean, heuristics can be very useful, right? But they're not. You're not solving the problem, right? And what's interesting about this, things like this, there are lots of other examples like this, is it turns out that sort of, your basic intuition about whether a problem is easy or hard, especially if you're not trained about, say, convexity, and we're talking about continuous optimization problems, right? If you're not trained in recognizing convexity, then basically your intuition is mostly just wrong. It's just wrong, right? The kind of things that you either got explicitly or implicitly from your 19th century mathematics training, right? Which is like small problems are easier than big ones. I don't know. Things, the smoother things things are, the easier they are. All of these are just wrong. They're just false. They're just not true, right? And worse than that, they're not useful, right? So, okay. That's actually one of the things we'll see in this class as we move forward. There'll be lots of examples of this kind of stuff. So let me say a little bit about what the course is about. So the goals are basically to get you all up to speed in recognizing these problems, right? So how can you, if someone has a problem in a practical context, and the question is, how do you recognize it as convex, formulate it, or in these more advanced settings, it's kind of the second tier or whatever, you would do something like this. Instead of saying that's convex or not, you would say that's not convex. But if we work with, and then you name some sick change of variables, it is convex, right? So we'll get to plenty of those too. And there's a bunch of those. They occur in all sorts of things. Actually, people trained in statistics and machine learning would already know this in the case of exponential families, right? Turns out the correct thing to estimate is not the covariance. That's wrong. Turns out the correct parameter to estimate is the inverse covariance. Even sicker, the correct thing to estimate is not the mean of a bunch of vectors. It's the covariance inverse times the mean. Okay? So we'll see all sorts of little cool things like that. You've already heard 2 from today's overview, right? Okay. So we'll also, at least in principle, in fact, not even just in principle, but we'll actually have you write up some simple code, and that's simple code for solving problems like these. You'll know how it's done. We won't focus a lot on that. That's silly because, well, there's quite good software done by people who know a lot more than you will know at that point. actually a lot more than I know about some of these things, and they've spent a lot of time doing this. So that it's not to replicate it; it's actually to demystify it. You'll be able to characterize the solution, a solution, right? And say what does it look like? You could say it's no better than this, and things like that. We'll see that. So okay, so the main topics of the class then are. For the first couple of weeks, we're going to look at convex sets and functions. I am going to warn you now, it's going to be dry. And what can I say? Too bad. It's all for a grander purpose because, I don't know, somewhere around week 3 or 4, it will actually then start getting interesting. And by 5, 6, 7, 8, we'll have hit our stride. And by then, by week 6, my claim is you'll have been paid back for what happened to you during the second, and third weeks. We'll look at a whole bunch along the way of examples and applications. Sometimes they'll be along the way just to illustrate something which is a theoretical thing, or sometimes it'll just be fun by itself. We'll just spend whole lectures looking at things like statistical models and things like that. We'll hold lectures looking at various things. And we'll also then do a section at the end which is on algorithms. And algorithms, how do you actually solve these things? And again, that's mostly to demystify these things because they're not that hard. Okay, so I do want to say a little bit about nonlinear optimization. And so this is these are traditional techniques for general non-convex problems, and they involve compromises. By the way, this is also called NLP, which I know clashes with natural language programming, but they actually had the acronym first for the record. So that's NLP. It's nonlinear programming. By the way, that's the kind of very much the Western view of the world, right? As all the stuff was developed in the 50s, 60s, 70s in the U.S., it was mostly and Britain and various other places. It was LP versus NLP. So linear programming versus nonlinear programming, and that was the conceptual view, and that's how people identified. That's who you would hang out with and things like that. There were a few others. There was ILP. That was integer linear programming. And they mostly didn't hang out with each other. Anyway, we'll move on. Okay, so here people use local optimization methods, and the idea is at the very least you find a point that minimizes f0 among feasible points near it, right? So at least you find if you come up with a circuit design. And they say, what's the power dissipation? You say, well, it's 82 milliwatts. And they go, that's pretty good because, last week it was 122. And then you'd say, well, and the idea is this, if you were to search around your design space near that current solution, the power would always either go up or you'd become infeasible, right? You move in one direction, and you would no longer meet your timing requirements. But you move in another direction, you meet your timing requirements and everything else, but unfortunately the power goes up, right, or something like that. So that's a local solution. Okay, and this is extremely successful. I mean, this can handle large problems. It can do all sorts of stuff. It can be fast. Unfortunately, what it requires is an initial guess, a good guess, right? So that's how that's done, and it kind of really turns it into an art. Not really science, which is great. So it's an art. And of course, when you do this, you're never really quite sure whether or not this is the best you can do because you don't know. Now, you may not care because, if you're taping out in 10 days and someone just reduced the power of some sub-circuit by some significant amount, your primary thought is not, my God, do you think there's another design that's like a little bit better or something like that? You're like, this is great. So this is fine. I mean, in some applications, it's in many applications, this is just fine. Okay. Now, the other compromise is to give up on speed. You don't give up on solving, right? So another way to say this is in local optimization, you kind of give up, you redefine solve to mean not solve, right? It's kind of a best effort thing, right? By the way, you can always do anything because you take a heuristic and around it, at the end, before you return the solution, you check if what you require that someone pass in an initial design or an initial point. And if after you've done some, you time out, you do whatever the hell, it doesn't make any difference, you quit. And you check if what you have produced is better than what they had. If it's not, you return what they gave you. right? So then you can do no harm, right? So then it's fine, I guess. All right. Now the other goal is the other option is to do this. You actually solve the problem. You get the absolute best. But now you're willing, and you will have to sometimes accept very long computation times, right? And in this case, the worst case complexity in theory grows exponentially with problem size, and sometimes in practice, actually fairly often in practice. So this is where you actually get the absolute best. You get something that absolutely minimizes the objective, right? Now, it turns out in both of these, well, certainly in global optimization, almost every method for global optimization is based on convex optimization as a subroutine, right? So, and we'll see bits and pieces of that as we go through the course. So let me finish up with just a brief history of convex optimization. So, bits and pieces, of course, trace much earlier than this in mathematics, right? Well, linear programming, is 200 years old easily. Least squares is whatever, 200 years old, maybe older. But the theory of it, was pretty well developed actually by about 1950, and by 1970 it was really quite well developed. I guess in math it's called convex analysis. That's the mathematics of convexity, mathematics of convex optimization. It's convex, and that was basically like kind of done in 1970, roughly. Now, algorithms for solving it, there have been lots, but I'll just mention some of the highlights. So the one is the simplex method for linear programming, and this is George Danzig, who was actually at Stanford. So this is from the 40s. This is also done at Moscow in the 30s, I should add. This is simplex method for linear programming, and actually the date is really interesting because it tells you something. It's basically coincident with the development of the modern digital computer, and that's what sort of makes this interesting. I mean, this was in 1940. All the material we're going to cover in this class, well, we couldn't have covered any of the applications, but all the material would be super interesting, very interesting mathematically, right? But when you throw computation, the ability to do computation and actually do stuff that has real algorithmic teeth, where you're not just writing down silly formulas or searching for silly formulas in vain or something like that, then it gets really interesting. And so it's not an accident that this is about the right time. Came right at the right time. It's a very simple method called simplex. It was propagated and used everywhere in the world. It's used in all over to this day. Okay. Now, part of something interesting in this class is in the 60s, there were some early attempts at interior point methods. We're going to study those in maybe the 7th, 8th week of the class, 8th and 9th, something like that. There were early attempts at these. So a lot of the stuff we're going to look at is not new. By the way, some is very new. So some of the applications and things like that are very new. Some is new. But a lot of it is not new. It traces to the 60s. In the 70s, there was work out of Soviet Union on methods called ellipsoid method and subgradient methods. We're actually not going to cover those in this class, but just it's another, I think, a very important milestone. A big one was in the 80s, and in the 1980s, you may even have heard about this. I guess AT&T was being broken up or something like that. Bell Labs was being pulled, was going out on its own, and somebody knew something, somebody who knew somebody else who knew somebody else, and an algorithm for linear programming ended up on the front page of the New York Times. Right, not front not the science section, front page. Okay, I mean, okay, maybe it was a slow news day. Okay, still, it was the front page, and sometime in the late 80s to now. There was just a whole bunch of things came together the right way, and there are people in the Soviet Union working on solving general convex problems, people looking at applications, and this all kind of came together, and it was great. So and things worked out. So the most interesting part is something like this: is before about 1990, there were plenty of applications. It was almost all linear programming. Right, and they were generally not. I mean, some were in engineering, but mostly they were in areas like finance, management, these types of areas. So they were in operations research departments. But what happened in the 90s was that more and more areas in engineering started using these things. By the way, a similar thing happened in statistics, I would say, that Up until 1990, it was still like you're doing, Fisher and analysis of variance and basically least squares and things like that. And that somewhere between 1990 and like 10 years ago, the idea that you would actually solve some problem to come up with a statistical estimate sort of became mainstream and has propagated very widely now. We'll talk about that in great detail. Um, but since then, there's just been this huge explosion in lots of areas, in engineering, but also in statistics, machine learning, and lots of other areas. So